So this was the problem that I posted outside today, right? Look, it should have been a straightforward problem, and it's okay if you didn't remember it, but whenever you see the word equation of a tangent line, as soon as you see tangent line, right, and you see this right here, when you write an equation of it, you're going to need a slope. Slope of a tangent line, you need to start thinking derivatives. And 7 times out of 10, problem probably needs a derivative, right? The other 2 out of 10 is going to be an integral, and the last 1 out of 10 is usually a limit problem. Most of these problems are going to be some way, shape, or form where you need to take a derivative, right? You don't know what to do? Take a derivative. If you don't know what to do after that, try an integral. That's basically the overall strategy for calculus, is integral, derivative. It's one of those two, unless it's a limit. Now, how do I know this one's a derivative? Again, tangent line and the slope of that tangent line. I already have a point right there. My equation of a line is actually going to be y minus 1 is equal to m times x minus negative 1. Do you see that? Yeah. And that part's fine. All you got to do now is find out what the value of m is, which is what's the slope of the tangent line at this point, right? To get the slope of a tangent line, you need to take the derivative. So we need to take the derivative of this, and we're going to do it with respect to x, okay? So what's the derivative of y cubed? 3y squared dy dx. Very good, very good. That right there, that dy dx, that's what's going to help you find your m. Okay? So you're going to do that every single time you see a y in this problem. So we're going to go ahead and go on to the next one. Notice that this right here is not dy dx 2x. That is a product of 2 functions. You have to use the product rule for this one. So derivative of the first times the second plus derivative of the second times the first, right? So, well, I'm going the other way. I go dy dx times x squared, right? Derivative of the first times the second, plus the derivative of the second times the first. You okay with that? Yeah. This entire chunk is coming from here, taking that derivative, okay? Moving it along, next derivative after that is going to be plus 2x dx dx, but dx dx is just 1. Minus 6y dy dx. And this is all, of course, equals to what? 0. Your ultimate goal is to solve for dy dx. Now, if it was asking for us to just give them the derivative function, you could do the algebra and solve for it. Get everything that has dy dx on one side, solve it, move everything over, right? And we could do that real quick here. Just let me see here. Let me rewrite this with only those terms as 3y squared dy dx. The other one is plus x squared dy dx minus 6y dy dx. Everything else that doesn't have those terms, which is this term right here and this term right here, I could just move it to the other side of the equation and write this as minus 2xy, yes? Yeah. Minus 2x.
I missed it.
Yeah. After that, factor out a dy dx over here from all of these. And what's left inside here? We got a 3y squared plus x squared minus 6y. Just divide by it. Move it to the other side. And we end up with this crazy looking fraction of dy dx equals to negative 2xy minus 2x all over 3y squared plus x squared minus 6y, but that's still not our answer because we still need this evaluated at, what was the point? Negative 1 and 1. And just plug those in for your x and y, and that's what's going to give you your slope.
No, I think you just start doing tennis so you don't see that on here, huh? Okay.
So, can you guys plug in 1 and negative 1 in there? See what you get. And let me take attendance over her. So, Devin mark as late. With a pass. With a pass. With a pass. Yep. So, the number that we are plugging in into this is negative 1, 1.
Oh my god. Oh, this is real.
So dy dx evaluated at negative 1. Wait, 1 negative 1 or? Yeah, negative 1, 1. So plugging that in, you'll get negative 2 times negative 1 times 1 minus 2 times negative 1 all over 3 times 1 squared plus negative 1 squared minus 6 times 1. Is that okay? Boop, boop. So we get 2, boop, boop, plus 2. Right there in the top, is that right? In the bottom I have 3 plus 1 minus 6. Does that look right? 4 over, what is it? Negative 2. So, negative what? Negative 2 over 1 or just negative 2? So what's my equation of my line? Y minus 1 equals? Ta-da! Now here's this thing though. If they ever give you the point to plug in for x and y, you don't need to solve for dy dx yet. You could just plug in the values for x and y at the very start. You know that right here I have my x value and my y value right here? Just plug it in now. 3 times 1 squared dy dx plus dy dx times negative 1 squared. You okay with that?
Yeah.
Plus 2 times negative 1 times 1 plus 2 times negative 1 minus 6 times 1 dy dx. Now this looks messy, which it kind of is. I'm going to take this over here and move this to the side right here. But check this out. Oh, knock me. Get over there, gently, gently. Come on, careful, careful, don't drop it. There we go. Check this out. If you solve this over here, watch this. 3 times 1 is what? 3 dy dx, yeah? Negative 1 squared is just 1, so this is also plus 1 dy dx. Negative 2, negative 2, negative 6 dy dx. What is this all equal to, by the way? 0. Solve this. Combine like terms. What do we get here? Oh yeah, you're right. We'll do that first. That's easier. Negative 4. And what else? Minus 2. The negative 6 like terms. This is technically a 1. You see it?
3 plus 1 is 4. 4 minus 6. That's negative 2.
We doing okay?
Yeah.
Help me solve this.
Add
4
4 to 4.
to both sides. Help me solve it. What do you get?
Wow. You get the same thing.
Yeah.
I love how, I got the answer and, I couldn't.
Oh wow. Oh wow. Oh wow.
Yeah.
I like it. That was nice.
So, do you need to do this long process to solve for dy dx? No, not necessary.
Wait, can you show the fraction?
Only if they don't give you the question. Oh my god, I love it.
So, 2 different ways of doing the same problem. Doesn't really matter which way, but usually if they give you the x and the y value and you're looking for a particular number, just plug it in. If they're asking you to find specifically what is dy dx, they don't actually say what value is it, they want the function, the derivative function, then you have to go through this process. At the same time, if they ask you for the second derivative, you need this to plug into the next part. So when students always ask me, like, do you memorize these processes? Like, not really. That's too many steps to know all off the top of your head. It's just one of those things, like, just try it. Like, if you have the numbers, try plugging it in, see what you end up getting. If you don't have the numbers, see what they're asking for and see if you can do it without having to do it. You know what I mean? So that's that problem. You guys okay?
No.
Not okay? Where'd I lose you?
I wasn't here.
Oh.
So just don't listen.
Oh, okay.
You lost me in August.
It just looks like, oh, yeah, I can show I would,
He's looking mortified. You look mortified by that comment.
I don't know what to, I just don't know what to say to that comment. Just like, that's a shame.
Yeah.
Is your back still hurt? No, you just gotta say me
Huh?
too. Is your back still hurt?
A little bit, but not in the same way.
You know what's been hurting me?
What?
My ankles. My malleoli.
Why has your ankles been hurting?
Because I think I jumped when I'm laying
Okay.
That's not pretty much.
So, last time we were talking about this, right? Position, velocity, and acceleration. We know the connection now, yeah?
Yeah.
Derivative of position is velocity. Derivative of velocity is acceleration. Now, if we go the other way and I give you velocity, you can find out position. There's two types of positions that they'll ask you. They'll ask you how far something's traveled, right? That's not this one though. This is displacement, right? Displacement from A to B will tell you how far away they are from where they started, right? It doesn't tell you how far they traveled. If we wanted to know how far they traveled, we'd have to do the absolute value of this because sometimes they go backwards, yeah? So we can take that into account how far they traveled. Now this is the other one, is basically where do you end up at, yeah? So this is how far they are displaced from A to B, but if you take into account plus where they were at to begin with, you can figure out where they end up at. Does that make sense, or does that just make it weird?
So position to find displacement, travel, and
How'd
where
you
they end up.
Say it one more time?
It can find displacement, travel, and where it ends up.
Yeah. Displacement is where the difference is from where it is from the origin, right? Whereas where it ends up can be a little bit further from where it started, right? Not just from where the origin is. Does that make sense?
Yeah.
I think I switched those around.
And then travel is absolute.
I don't think. No, wait, like 5 minutes.
All right. So, did we start a problem? We did, right? Right here.
What's it doing?
It's glitchy. Of course, when I want it to glitch it, it doesn't do it.
Oh my god, it's easier.
It's like an overload. Come on, calculate and fix it.
All right. So, check this out. Write an expression that involving an integral that gives the position of s of t. Use this expression to find the position at particle time equals to 3. So here it is, right here. Right? It's going to go from 0 to 3. That's going to give me the displacement from when it starts moving up until 3. And then I just add where it was originally at the start. So that way I can figure out what is its position at time equals to 3. Okay? Does that make sense or does that not make sense? The general idea of this, like the big thing that I want you to grasp is the fact that what do they give you? What's the function? V of t. It's a velocity. The fact that we need position means that we need to do the integral. Yeah? If they had given us position, we don't need to do the integral. We're good because we have the position function, right? If we're given position and they ask for velocity, then we need to take the derivative of that position function. Does that make sense? We're at the point now where you need to know, am I going to take the derivative of something or am I going to take the integral of something? Does that make sense? We'll worry about the plus the origin part later. Just realize that that's the idea here. We're just trying to figure out where. Yeah? All right. Anyways, let's actually just finish up this problem right here. This is a calculator problem, meaning you don't need to do this integral by hand. And thank goodness we don't, because look at this function. It's going to go from the integral from 0 to 3 of t minus 3 ln of t plus 2 plus 2t times sine of t squared over 12 dt. I would. Wait, did you not write this down last time?
No, you asked us not.
Don't write it down then.
She's that already did it.
Okay.
Do we do it or no?
You write it down. Write it down.
Down the bottom part.
Yeah, just copy down the bottom part. And copy down the bottom part and copy down this equation up here.
And how about
Don't write the words. Just write down the equation.
Here, look, I'll give you a post-it note.
Wait, copy down the bottom part?
Post-it note.
Yeah.
Oh, never mind.
Don't worry.
You just wrote and then copy the.
Yeah, don't worry about this part.
Ah!
Okay, I just crammed it all in.
You don't even use the post-it notes.
Because I have this, but she uses it.
Maybe if she would have freaked me out, it would make more sense. But
I use it for
So,
my
write down
tech class.
a particle moves along horizontal.
It's just
Or
you don't have to. Just get the equation.
The VT.
Yeah.
damn it.
Can you use like 5 minutes to write this down?
I'll give you 2.
We need like 2. Then
Speak for yourself.
you must like say my name.
I can't. That's nowhere.
Yeah. I can tell. It's always in your mouth.
There's always a way.
Okay.
Alright.
That makes me mad.
Oh no. He's recording, Devin.
Oh, he is. Oh.
Just stop.
I didn't say that. That was my.
You're not a good person to be yesterday. Oh, yesterday? That was not me. That was not just me. It
Alright.
was Juan.
Wait, what? It was small.
The
Alright.
filter.
So
Oh, quantum
Do me a favor. Sharpen that.
this part right here, this entire thing, this integral right here, it's just this part, right?
Can you go back up real quick?
Just a little
I
bit.
didn't even know you were sharpening the fence. That's the funny part.
So
Thank you.
Okay, thank you.
yeah, the big thing I just want you to be able to see, right? The function they give us is a velocity function. They're asking us about position of something. You have to realize, like, to get the position, we just have to do the integral. Okay? Now, here's a bigger thing though. The integral that we're dealing with, right, is usually between some time, like how much time it travels. So from when time starts to time finishes. And how do I know time finishes here? Because they're asking us to figure out where it is at t equals 3. How do I know to start at 0? It's going to vary from problem to problem. Okay, in this case, I know that this problem's starting at 0 because they tell us like t is equal to 0 at the start of this problem. Not only that, it says right here, at the start of the problem, t is equal to 0, what's the position?
3.
Negative 3. So, to add to this problem, I need to add what? Negative 3. So, the thing that I have highlighted in blue, what that is essentially going to tell me is the displacement of this particle from 0 to 3. So, after 3 seconds, it'll have moved at some random velocity, and then at 3 seconds, we're going to record where it ends up. Where it ends up compared to where it started is the displacement, and this thing in blue is the displacement. Does that make sense? Like this integral is just the thing that helps you calculate how far away it is from 0 to 3.
So this is going to be our equation, one of our main equations?
No. This is just this example.
No, I'm saying, but like that, the S of t equals to.
Oh yes, this?
Yeah, just
Yeah.
the integral of dt.
Yeah.
Okay.
I'm gonna give you a list of these things.
So will there always be an S of both in our equation?
Yeah. Depends. Again, it all depends on what they're asking for, and if they're asking you for position, usually there's an S in both of them.
Okay.
Because you need to know where it starts.
Right.
Now,
So-
here's the kicker, right? Here's the kicker. You guys got that written down?
Yeah.
I'll give you a second. Give them a second to write this down. But there's actually a neat little like connection to what we've just learned. So, you know how we've been doing integrals, and it usually goes from like a to b, and it's like of some function, right?
Right.
And we get our answer, right? And it comes out where we have to plug in. Knock me. We have to plug in a and b. Yeah?
Right.
And then I showed you we could also do the same thing, but with no a and b.
Okay, yeah.
When there's no a and b though, we end up with this thing, but we also end up with something afterwards.
Yes, I'm with you.
You okay so far?
I'm with you. I'm with you.
That plus c is usually what that initial start is.
Oh, okay.
So this idea, right, is that if we did the integral of a velocity function,
Sorry.
Are you good?
I thought I said it in my head.
if you do the velocity function and you're doing the integral of that with nothing there, that's essentially equal to the position function plus c. And that c is where you start.
Right.
That c right there is
Oh.
usually where your s of t
Understand.
starting is.
With the interval for 0 to 3, do you get the 0 from the S of 0, or do you get the 0 from the
S of 0. S of 0. And it's also connected to that 0.
Yeah.
So usually, whatever that number is going to be the number that's in here. Usually. Another thing is sometimes that they don't give you 0. They'll give you like 1, and it'll just be this thing that you add on at the end
Okay.
to give you that function.
Because like there's a negative and positive. Even though it starts at 0, it's always has that 0, but you changed it to 3 because it told you that it starts at 1.
Mhm,
And then you
mhm.
added.
Okay, there's this page of shortcuts on these position, velocity, and acceleration notations. I'm going to put it onto the screen. I don't want you to write it down. I'm going to instead get a copy of it and put it online, and then you guys can print it out.
Oh.
I should just print it out for you. But I'll probably get it printed out for you. But you can print it out yourself as well. But let me show you what this looks like before I move on here. And I'm going to put it in the notes online right here. And then I'm going to get a nice printout for you later.
Is it 31U or 31N?
What?
That's
Oh,
shit.
3LN. 3LN. Sorry. Anyways, I would plug that into a calculator and just see what you get. But we're not going to do that right now. Yeah.
Finally got a blue highlighter, and the second that I did, it beaded, like it bled all over my pencil card.
Oh my god.
So we're not gonna solve this equation?
Oh, you just plug it in the calculator at this point.
Okay.
Yeah. So since there's no way you can do this one by hand. I don't know the integral of 2t sine. All right.
So wait, question, one more question before we go. Before we plug, when we were to plug this into the calculator, we can plug it and ask it.
Yeah.
Do we have to, like, you don't have to do any answer or anything?
It will do. The calculator should do it for you. Remember, what's the function to do the integral on your calculator is math 9, right?
Yes, okay.
Fn int. So you plug that in there, and that should be good. All right. So real quick, let me show you this. Don't write it down. I'm just going to show you piece by piece here. Whoa. Okay. So.
Look, wait, can look at the picture I took right now.
Nice.
I don't know if you can see it. Hold on.
I saw it. Just take it again. I'll put it
No,
right
I know I did, but
Oh, okay.
I thought it was funny.
All right. So.
Why are you laughing now?
Not that fun. So we got position, velocity, and acceleration, right? Usually when they say initial, it's usually like at t equals 0. But again, that can change from problem to problem. Like, are we looking at it when it starts at t equals 0, or are you looking at it when t equals to 3? Time is just moving from 0 to whatever it needs to get to, right? So if you don't want to care about from 0 to 3, if you want to care about from 1 to 5, your initial value would be at 1. Does that make sense? It's just where are you starting to look at this thing?
Right.
What time is it at? Now, there's some expressions here that, like, they're not calculus involved, but it's just stuff that you hopefully should know. Like, for example, if a particle is at rest, meaning it's not moving, the velocity should equal to what? 0, right? If the particle is moving to the right, that usually means that the velocity is positive. If it's moving to the left, then the velocity is negative, right? But those aren't the big ones I want you to see. The big one I want you to see is, where is it? Here. Instantaneous velocity is just the derivative of the position, right? The acceleration is just the derivative of the velocity, right?
Didn't we kind of like do something similar to this earlier in the year?
Yes, yes, yes.
Oh my goodness.
Now, the reason why I'm bringing this back is because of the other, there we go, the other way, which is basically
That
now the
matches your shirt.
integral.
Hey, look how the glasses.
The integral, right? The integral of velocity is going to give you the displacement of the particle or the net distance traveled by the particle over some time. So let's say at t equals 0, I go forward 3, I go back 3, I go forward 3, and I go back 3 by the end of my interval. How much displacement am I at?
0.
Good. And so what would happen if I took that integral and, recorded that velocity? Positive velocity, negative velocity, positive velocity, negative velocity, 0. If I was looking for the total distance traveled, you have to do this with the absolute value of the velocity. Meaning whenever velocity turns negative, you just make it positive and calculate the area there. So what does that look like? What does that entail? If I was looking at, remember, integral is the area underneath the curve, yes? If my velocity is positive, my displacement is going to equal to my total distance traveled, yeah? If my velocity has some backwards in there, if I go up and then I go down like this, my displacement is going to be whatever this is minus whatever this is, right? Does that make sense? Mm-hmm. If this was, let's say, 5 as my area, and this was 4 as my area in there, my total displacement would be 1. Does that make sense?
Yeah.
But what would be my total distance traveled? 9. That's the idea. So the hard part for this for most students is, that makes sense conceptually, right? Like you just add those two areas together. How would you do that using an integral, right? How would you do that using an integral of v of t dt? It is the absolute value, yeah? That might be not too bad, but how do you calculate, how do you do that algebraically? You would do, yeah, how would you just calculate it? So let's say this function right here is v of t. Hopefully you can see it. You need to calculate the integral from here to here. Does that make sense? Get that, whatever that would be. So from a to b, and then do the integral from b to c, right here. Yeah? And you could do the absolute value, or what I used to do was take it, realize my answer is going to come out what? Negative, and then make it positive. Does that make sense?
Okay, I get you.
Wait, so you added a C.
Yeah, those are just random points. Yeah, but that's the main thing I was trying to get to you from here. All right, and then there's that position equation again, right? They do s of t. They put it in front, but I put it in the back because I like to relate it to the plus c that we've done in the past. Does that make sense? All right. You guys okay with the whole position, velocity, acceleration idea? Yeah? Not too bad? Okay. Don't worry. We didn't write any of that down. Okay. Let's see here. Okay. Let's do this one. Let's say a function is a graph instead here. So let's go with this one right here. This one I do want you to copy down, okay? So if you guys could. Let me zoom out a little bit and then, too much. And make that a little bit bigger. Yes, please.
Okay.
The Space Shot is an amusement park ride that gently raises riders up a tower and then rapidly bounces them up and down using compressed air. What?
That was you.
Rapidly bounces them
She would've said something.
up and down using compressed air. The velocity of the Space Shot for 0 less than or equal to t less than or equal to 14 is modeled by this piecewise linear function shown below, where t is measured in seconds and v is measured in feet per second. So this is a graph of velocity. This isn't a graph of how,
Sure is.
where the position is, right? It's not saying that, at t equals 2, that it's at 20 feet above the ground. What it's saying is that at t equals 2, this thing is traveling 20 feet per second in the positive direction. When I'm looking at it at t equals to 6, this thing is not moving. It has a velocity of 0. And then after t equals 6, when I go down to t equals 7, it has a velocity of negative 60 feet per second. That means that it's falling at a rate of 60 feet per second, right? So it's being raised slowly, and it gets to here, and it's continuously being raised all the way up until 5. After that, it's slowly being raised still. It's still positive. Even though it has a negative slope, it's still being raised, right? It's still being raised at a positive slope, and then it gets to here at t equals 6, it reaches the top at 6 seconds. After it reaches the top at 6 seconds, what happens? Velocity now turns negative, which means the ride is now doing what? It's going down. It's falling. It's falling from 6 seconds, 7 seconds, and then at 8 seconds, it stops falling. It's hit the ground and everybody's dead.
Oh.
No, that's not the case. Why is that not the case? Because what happens after 8 seconds? It starts going which way now? Up. So what happened? It went all the way down, reaches 8 seconds, and then what? It slingshots back up for the next 8 seconds, 9 seconds, 10 seconds, and then what happens at 10 seconds after it reaches it reaches the top again, it stops going up, now it changes back to going down, and it's falling down, slows down to here.
Is it like 10 seconds or is it 2 seconds that it goes back up? Right?
It's traveling for 2 seconds, yeah. But between 8 to 10 seconds is what I meant to say.
That's not too bad.
You want us to draw that too?
It would be nice if you did. It would help for these next couple of problems.
Is this gonna take up a lot of space?
Yes.
Yusha is holding us
I
soon.
use a sticky note.
Good. Yeah, it's gonna take up a lot of space, man.
I'm still on the problem.
Me too.
Me too.
I mean, Yeah, you're still on the description of the problem. You haven't gotten to the this part of it. Are you ready for this part of it?
No.
The question part?
I
No.
literally just finished writing the problem.
And we had to do the graph too.
You don't have to, but it makes it easier for you.
Matthew, can I ask you a genuine question?
Sure.
Do you hate us?
No.
Okay.
Why would you ask that?
The
Huh?
what?
Well,
Wait, does he what?
I know, I feel that question. Just,
Mr. Malcolm, you know you can print some of these things out, right?
What's up?
So you know you can print some of these things out, right?
Press some of these things out.
You can print some of these things out, you know that?
Oh, I can print some of these things out.
Yeah.
I thought you said press.
Oh my god.
Not
That too, press the printer.
Who's not me? Do you eat 7-Eleven food?
I have. I don't eat it now, but I have. Yeah, it's really good trashy food.
How'd you eat?
What was it? Taquitos? Is it the taquitos?
I like the pizzas and the hot dogs.
I never had the pizzas or the hot dogs. I've only had the.
The pizza has pretty good
The
cheese
pizza's
on it.
good.
Yeah, the pizza has
One
good
Direction?
cheese.
Wait, what? 7-Eleven?
It just depends. Like some days it'll be burnt and some days
Yeah.
it wouldn't. You just gotta look at it.
I only got their slushy.
They just came out with cookies, like they have a box full of cookies, and they're surprisingly really, really good.
I ate their cheeseburger once and I had a stomachache like bro.
Ew, I would never do that. No, no.
So I want you to try to answer A on your own. At what times in the interval from 0 to 14, if any, does the space shot change direction? So just looking at the graph, just see if you can, don't shout it out, just write it down. See if you can figure out when it's changing directions.
Wait, so if it's a piecewise linear function, does that change anything?
No. It's just describing the graph for you.
Pretty sure you're done.
Hang on. This is.
Oh, that's sure.
This graph. I'm trying to nail it.
Wait.
I gotta imagine this.
Of them bouncing up and down.
So do you just have to list the times?
Yep.
So wait, are the is velocity? There you go. Never mind. That's the only question.
It's not a graph of position, is it?
Graph of velocity.
It is a graph of velocity. So this is the graph of velocity. So when is it changing directions? At what times?
Actually, the first method.
You guys written down the first paragraph already, right?
Yeah.
I'm gonna scroll it down, okay, so we can get a better view of the question. We'll look at the graph though. Well, in this case, the y values is your velocity. When does this thing change directions? T equals to what?
Wait, at the beginning, so like when we count from where it starts at the no, okay.
Nah, it just started moving. So it's not changing directions, it just started moving at 0. What do you think? Devin, what do you think? Give me one that's in your mind.
I got T equals 6.
Let's pause there for a second. That's a pretty good answer. T equals 6.
From 0 to 6, it's going one direction.
Yeah, from 0 to 6 it's going which way?
It's going up.
Yeah.
Well, it states at a constant of a positive the velocity, so it has to be going up. I think.
So here's the thing. That's one of the hard things that people have to see here. From 1 to 5, it's not staying still. Its velocity is constant. It's still moving, but it's moving at a constant speed of 20 feet per second. It's like when you're driving in a car and you don't accelerate, right? And you're going in your car at 30 miles per hour, you're still going forward, even though your velocity is constant. That's what's happening here. This velocity is constant. It's just going up. And then when it goes slightly down like this, it's still going forward, isn't it? It's still going up. It's slowing down, though, until it reaches this point right here, where it changes from positive to negative.
Okay, but technically, couldn't you also say 1 and 5? Because it moves from 0 to 20 at 1, and it moves from 5 to 0 at 6.
Moves from 5 to 0 at 6?
I mean 20 to...
Yes, but it's not going in the other direction. It's so like picture you're in a car and you're going 30 miles per hour. Yeah? And then you start going 20 miles per hour. And then you start going 10 miles per hour.
Yeah.
Then you start going 5 miles per hour. You haven't changed directions yet, have you?
Oh, that's changing
Slow.
direction.
Yeah.
Slowing
When I reach here and I go to 0 miles per hour, I stop moving. Yes? And then when I start going to negative directions, or negative velocity, I start going the other direction. So I change directions from here to here because you're changing signs,
Oh,
right?
that makes sense.
It's gonna change directions for you.
Hey, you learn AP physics.
In this case, it's only 3 times. T is
Oh,
equal to
yeah,
6.
'cause, well, you start initially at positive, so it's not changing.
Yeah, T is equal to 8. And T is equal to what?
10.
10. What would be my reason? Right?
Because the sign.
Yes, that's exactly it. The sign
Oh, okay. I had.
of
okay.
the velocity
Oh, that makes sense.
changes
That makes sense.
at each of those values of t. Did you know what we called those points back when we first learned about this type of thing?
Critical point?
Yeah, they are critical points. Not only are they critical points, they are possible max and mins, aren't they? They're extreme values, right? If they change signs, it's possible that it's either a max or a min there, right?
I have ideas, Mr. Nine, but really in AP Calc.
I think you guys have more days than you know. You guys just don't realize it.
Hopefully the 9th of May is one of those days.
You're smart every day.
That is coming up. Oh my goodness. Literally my birthday is surrounded by a whole bunch of AP tests. I
When's
have
your
an AP
birthday?
test on my birthday, Mr. Malcolm. Can you believe that?
What day is your birthday?
May 12th.
Wait, who?
We have
Oh, yeah,
AP
my
lit on my
birthday's
birthday.
that day too.
Oh.
Wait, you took AP Lit one?
Yes, on May 12th.
That's okay. You'll be taking that, and then I believe after that you'll be done.
No, I have an AP physics exam too.
AP Physics is on.
Don't even try on that.
Is that the
What
4th?
percentage of passing?
Yeah,
is really
I think.
Well, that's why you try.
So
There's only one
you have this is the first week of AP tests, and then this is the second week of AP
And then we're
tests.
done. We're free. Oh my
That's
god.
I think-
That's AP lit. And 12 is AP lit.
SBAC is here, right?
Oh no, never mind. We're not
That
done.
And then we gradually
SBAC is easy.
Then we
Oh.
do.
Look,
The same.
You
yeah,
graduate.
like it's really
It's
fun.
Eleven.
Yeah. But you guys are gonna do fine. The questions on there are like, actually, how good are your algebra skills?
We've been focusing too much
Actually,
on
business
Calc.
You'll be fine. You'll be fine. No. All right. So let's go over here. Boop 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 boo.
Can you give us an example of something that'll be on the SBAC?
Yeah, actually that would be a good idea, huh?
We don't have to take that, right?
Because
They
taking
go
that.
to algebra 2 and I'm
We
like,
just have to take the science one, right? We don't have to take the math that's back?
Yep.
Oh, okay.
wait, we don't have to do that.
I said seniors not to take the math one, but we have to take the science that's back because they want to see how we excel.
You want to say that again in that tone?
We didn't
They
know.
want to hear how we excel. That's literally what she said. I was like,
I'm gonna move this over to the
"Miss,
side."
taking this exam. She was like, because we want to see where you guys are at. No, you don't. You just want to watch us fail.
I mean, isn't that the same thing as seeing where you're at if they want to see you fail?
Basically.
Fail.
But
All right.
just don't make it sound nice. Be honest about it, you know. we wanna make y'all fail.
Well, I mean, it doesn't hurt you if you fail that test.
Yeah, but colleges see it. It's gonna hurt
No,
them.
doesn't it hurt you when they're choosing your classes?
No, then you just have to take the remedial class.
And who's
Then
trying to do that?
that's just more money you're wasting on those classes, right?
If you test and you can't prove that you know this stuff, should you really be going into the higher level classes of science?
Yup.
I don't need it, standardized.
You'll end up struggling more.
But is it our fault though?
What?
That we don't know. If something is on that test that we don't know, is that our fault?
I don't know, but then if you don't know it, should you be going into a class where they expect you to know it?
Yeah, but not.
True, but isn't that what these
Learning
classes
about.
are for? To prepare us for a
Right.
college class so that we don't have to take remedial classes?
Yeah, if we can only figure out some way to find out how much you know. Oh, I got it. Let's take a test so you can see how much
No,
you've
no,
learned.
no, no.
But standardized, okay, this is what was on the practice aspect. The standardized tests don't measure intelligence.
They don't.
Then what's the point of them?
To see how much you know.
Yeah.
How much you know is not what measure your intelligence.
but it's
No,
like-
you don't. You just said that they're
No, I
different.
understand that.
No,
I'm just
like-
saying, but like,
It's just like what it's testing your test-taking abilities, not your knowledge
what
on
you
that
know.
subject.
'Cause if
It's
you
close
learn
enough.
it-
How else do you want to test somebody on how much they know of something?
yeah, I
then?
understand.
You're
that part.
complaining, but you're not getting any solutions to
I
this.
understand that part. My
Does that
point
make
is
sense?
just,
Like,
Yeah.
you can complain all you want, but just
how
know,
do you
like,
make
we
it
got
so
nothing
that
else
these
better
kids
than this.
know? You know, like, how do we make it so?
I mean-
I feel like our stuff, that our curriculum is just like set up to pass high school, no, not to help us in college.
Oh, just wait till you get to college.
So when it says the highest,
Yep.
is that only positive or can it be negative? Or do we have to take?
No, I want the highest. Negative would be the lowest, wouldn't it?
So it's not a trick question, right?
No, not a trick question. I want to figure out where the highest thing happens. And remember, we talked about this before. Highest happens at the critical points, yeah?
Yeah.
So, critical points are where on this case?
The 9 and 7.
What?
And wait.
6,
are you
8,
adding
and 10.
6, 8, and 10. 9 and 7 are the highest and the fastest and the slowest. Not slowest, fastest in the other direction. Remember, this is a graph of velocity, yeah?
Yeah.
If I want position, like how high it is, I need to do a little bit of calculus. Now, I know that it's supposed to happen at these values, at t equals to 6, t equals to 8, and t equals to what? 10, yeah? Now, that's because those are the critical points. But if I want to get the position of where they are and where they're located, I'm going to need to do the position function. Well, I don't have the position function. I only have the velocity function, don't I? So if there was only some way I could find out what the position is at t equals to 6, how could I find out the position of something if I only have the velocity?
Derivative, yeah.
Oh, so close.
Anti?
Integral.
The integral.
Didn't you say it's if you have velocity?
Yeah, because I have velocity right now.
Because you have velocity.
This is a graph of, remember, what? Velocity. If I would need position, position is going to be equal to what? The integral of your velocity. So I need to do the integral from when it starts till each of these points and see what I get for its position. So the first one's going to go from 0 to what?
6.
Of my velocity function, dt. And you'll say, crap, they didn't give us a velocity function, did they? No, they didn't. But they give us a graph. And I'm looking for the integral of this said graph from 0 to 6. What would that look like?
Oh, the shaded area. So we're going to oh, the
Trapezoid? Do we have to do
trapezoid.
a trapezoid?
Or no,
You have to calculate the area.
Oh, so
area.
trapezoid?
Yeah, that's what I was trying to say.
So let's calculate this area real quick. You could do it as a trapezoid, or you could do it like a nice little, rectangle right here and two triangles. You could do something like that. Also, notice the units, by the way. This is not going to be 1. It's how much is it in the vertical sense?
Oh, 20.
20. So what it would be the area of this thing? Well, this is going to go from 1 to 5. So what is that? 1, 2.
4.
That's 4. Yeah, you're right. You're right. So
4 by 20,
so what is that? What's 4 by 20?
which is 80.
80. Plus, give me the area of the triangles that are around it. What would the area of this triangle be?
10.
Has a height of 20, has a base of 1. So I'm 1/2, so it's 10 on that one, which is also what over here. So
100.
what's the position at t equals 6?
100.
100. Now, you'll say, Nakmi, didn't you tell me you're supposed to add where it initially begins as well? And yes, you are supposed to add it, but where is it beginning at?
0.
That's 0. It's at the start of this ride. So it's going to be 100 plus 0. So at t equals to 6, it is 100. How fast is this thing going? Is it feet per second? So what would the unit be for this, by the way? It's 100 what?
100 meters.
Velocity is given in feet per second in this problem. So what would my position be? 100? Think about it, what you're answering there. Position, it would be 100 feet.
Oh,
That make sense?
Sorry.
No, no.
Disregarded, so like, if you could.
You said something about a 0.
When you do position, it's going to be this right here plus the initial. I can't spell initial apparently. Position. But the initial position is 0 in this case because where you're starting, it's at the very origin. So the initial position would be 0, so it would be 100 plus 0 feet.
Oh, so then for the other next one, we're gonna have to plus 6.
Well, no, it depends on what we do our integral from and to. Now, if I do my integral from 6 to 8, then yeah, I'm going to have to say, oh, yo, where did it end up at? It ended up at 100, right? So.
Wait, what's the
Yeah, sorry.
so
That
we're doing the next one. And we're trying to do the integral from 6 to 8.
So you could do from 6 to 8, or hear me out. If I'm looking at it from the time is equal to 8, I'm looking for its from its position. I could just do this. Just do this as the integral from 0 to 8.
Okay.
But I like what you were going. You could also do it the way you were thinking. Go from 0 to 6 of my velocity, right?
But wait, I have a question.
Plus 6 to 8.
Couldn't you also do it from 6 to 10 because both those two triangles?
We are going to need to do from 6 to 10 as well, yeah.
We can't do that.
Yeah, we're going to have to do it to 10 as well. Because what are we trying to find, by the way? We're trying to find what? No.
The shot is the highest.
We're trying to find the position and at the highest point, yeah? So when I do it this way, this gives me that the position at t equals 6 is 100 feet. That's a good contender for our highest location, yeah? Let's do the next one here. I already figured out this one. The integral from 0 to 6 is just equal to what? 100. So that's equal to 100. We're done with that part. Plus, let's do this integral from 6 to 8. How the heck can we calculate the integral from 6 to 8?
A triangle.
You see the triangle?
2, oh, the negative 60 height.
Yep.
So it's going to be negative 30.
So it's going to be 1/2 times 2 times negative 60. Where'd you get the negative 60 from?
From the velocity.
Yeah, you see it right there? That height right there is negative 60 down, right? So what is my position going to be on this problem?
Negative 13.
100?
I lied.
Boop, boop.
Wouldn't it be
Minus 60?
60? Yeah.
So what is it in total? Well,
40
this will be at 40 what?
feet.
So I can already tell you at t equals to 8, that's not the highest position, right? Nita.
The function of a triangle is 1/2 times 2 times base.
1/2 base times height.
Base is
The base in this case is 2 because let me show you. The base is 2 because it's from here to here. Yeah, and then the height is this.
Oh, we also go back down. Do we have to add the initial to this one even though it's
Well, what's the initial? It's still at 0, right? Because what are we starting at? Yeah, yep. How we doing? You okay? It's weird, I know, but it's not that crazy. It's just these are the concepts now of what we can do with integrals, if you think about it, right? If you have velocity, integral will get you position. Yeah. So technically, the position, the displacement from 6 to 8 is negative 60. Because at 6, well, here's the thing. Where's it at right now at 8 seconds? It's where? 40. So picture this, right? Let's say this is 0, right? And this is me moving up, yeah? So from 0 to, let's say, 6 seconds, I'll be at 100 feet. Pretend this is 100 feet. Yeah? So from 0 to 6, the position now at 6 seconds is at 100 feet. The next 2 seconds, this thing's starting to fall, yeah?
Yeah.
How much does it travel from 6 seconds to 8 seconds?
40.
No.
No, oh,
I mean,
60.
60. And then at 8 seconds, where am I now?
40.
Yeah,
40 feet. Does that make sense?
Right.
So that these integrals basically just tell you the displacement, right? It tells you how much it travels. And the displacement from 6 to 8 was negative 60 because it went backwards with that negative velocity. That's why that area was down here. Okay? We're almost done, I promise. We got to do one more because what was the other critical point we're supposed to test? 10. So if I was going to do this one, give me the position at t equals to 10. Well, what's that integral look like? It's going to be the integral from... Now, here's the thing. We've already done 0 to 6. We've also done 0 to 8, if you think about it. So I would break this down like this. I would not break this down as 0 to 6, 6 to 8, 8 to 10. That's too much work.
0 to 8.
Yeah, just do it from 0 to 8 of v of t dt, because we already got that answer, by the way. What's that answer?
40.
Boom. And then just add the remaining 8 to what? To 10 of vt dt. Well, go look at the graph. What does it look like from 8 to 10? It's another triangle, isn't it?
Yeah.
Well, I'll pause there for you to write this down, and then we'll go look at the graph and see if we can calculate the area of that triangle, which I think is going to be positive now, isn't it? Because it's going forward. Ah. Ready? Yeah? Let's go take a look. From 8 to 10, what's that triangle look like? Has a base of what?
2.
Base of 2. Has a height of what?
40.
So let's go do that real quick. So this right here is equal to 40 feet. We already got that one. Plus, let's do this one right here. It's going to be 1/2. Base is 2. Height is what? 40. So what do I get as our answer? This cancels out. This cancels out. I'm left with 40 plus 40, which is an equal to what? 80 what? 80 feet. Now that I know these positions at these times, can you picture this ride in your mind a little bit better now? Have you seen this Supreme Screen ride?
Yeah.
Picture it. It starts off at 100 feet, right? They drop you. You start falling. But you don't fall all the way down to 0 because you die. So you fall to this a little bit before 0. You fall down to, it looks like it was, I gotta go look at the graph. Yes, to 40, right? So, yeesh. So, you started falling at 100 feet. You start falling, you start falling, you start falling, you're still falling, you're still falling, you're still falling, and you stop falling right there at 40 feet above the ground. After you reach that 40 feet above the ground, this thing starts to slingshot you back up. So you start going forward again, and you're going forward, up, 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 until you reach here, and you stop going forward, and you reach this height of what? What's the height at t equals 10? We just,
0.
it's 80. The
80
speed is
side.
0, but the height is at 80. Does that make sense when you've seen those rides? Starts at the highest point, it drops you, you slingshot down, and then do you go all the way back up to the top? No, you go all the way back up at just a little bit before, right? And that's what's happening here. After that, what's going to happen on the ride after it reaches that top of 80?
It's gonna stop. Come back down.
It's not going up anymore, and now it's going to start coming back down until it reaches to here. And I don't know if this is going to be at 0, or if it's going to be at below 0, or it's going to be right above 0. We'd have to calculate this area and compare it to this. And what I think should happen is it should come out to 0 if this is a well-designed ride. If it doesn't even come out to 0 and it goes below it, I mean, some people die. Right? Oh, okay, we could go the other way. If it's stopped a little too high, then some people are stuck. Then
Yes,
they
that's
die.
not like the
Okay.
So at the end of everything is a thing.
Okay. Are you guys okay with that connection there, though?
I'm fine with people.
What?
All right, Anita?
So the graph, you were explaining it goes from 100 to 40, it goes back to 80. Wait, that makes sense, never mind.
You sure?
Yeah, it makes sense, I just connected it now.
Okay. All right. Anyways. So if I wanted to find total distance that this slingshot travels, I'd have to turn these areas down here and make them what? Make them positive.
Oh, never mind.
And then just add it to the areas up top, and you can calculate what's the total distance this thing travels. Does that make sense? Right now, what we're doing is finding displacement. We're finding it where it ends up after a certain time. And that's just the position, okay? All right. How do you feel about that? Is it okay? That's the connection I need you to make now. Like the fact that you've seen position, velocity, acceleration, you know that derivatives go one way. Now I've given you a tool that makes it go in the other direction. Does that make sense? If I give you velocity now, you can actually find position. Yeah? Whereas before, I had to give you position to find everything else. Now I can give you anything else, and you can find everything else. Okay? By the way, if I ask you, hey, what's the acceleration at t equals to 3? What would you tell me? What's the acceleration at t equals to 3? It would be 0. How'd you know that? This is a graph of velocity. How'd you know the acceleration? What's constant?
The velocity.
Oh, okay.
So when you take the derivative of that,
There you go. That's what I want. The acceleration is just the derivative, which is just the slope of a line. Yeah? So tell me, what's the acceleration at t equals to 1? Right before it equals to 1.
1, 0, 20.
Positive. It has a positive acceleration, yeah? How about here?
Negative 20.
Negative acceleration, negative 20, right? Velocity is positive, acceleration is negative. Is this thing speeding up or slowing down? It's slowing down. You can see it slowing down. Crazier thing is this. My velocity here is negative. My acceleration is negative. Is this speeding up or slowing down?
It's speeding up,
Speeding up. You're falling faster this way.
Whoa.
This side, velocity is positive. I'm sorry. Velocity is negative. Acceleration, though, is positive. That means you're slowing down. You're falling, but you're falling at a slower rate. Picture yourself on that ride. When you start dropping on that fall, you fall pretty fast until you reach this spot where you're still falling, but you're falling slower. You feel it? Can you feel yourself on that ride where you're falling, but you're falling slower until you stop? When you stop, that's this point right here. You see that? It's not this point. You're not going back up yet here.
Velocity.
Yeah, you just start to slow down on your drop here. So when your velocity and acceleration are the same signs, you're going fast. You're falling fast. And then when your acceleration is not the same sign as your velocity, you're falling slower. You can feel it, right? It's like pulling you, but it's pulling you slower until it stops pulling you. Then your acceleration and your velocity are the same direction, and you start getting launched back up faster. You're speeding back up until what happens when you start going up? Eventually, you slow down, right? Your acceleration is negative now, but you're still moving up until what happens? You reach a stopping point, and then you go back to falling. That's position, velocity, and acceleration all in a nutshell. It's a lot going on, but it's a thing that you can just break down piece by piece. Does that make sense?
That makes sense.
Don't try to do it all in one go. Just kind of understand that's what's happening in these things, right? If they talk about something moving, break it down to what you need to find. Do I need to find out where it ends up? Do I need to find out how fast it's going? Do I need to find out its acceleration? Okay? Make the connection there. Realize that position's derivative is velocity. Velocity's derivative is acceleration. If I give you velocity, how do you get position then? Integral. Just go backwards. Make sense?
So velocity.
Velocity is usually in the middle. So if you do derivative of velocity, you get acceleration. If you do the integral of it, you get position. If there is a cheat sheet that you would ever take from me, is this would be the cheat sheet I would give you. Oh man. Okay, just I don't know if this is gonna help you or make it worse for you. No, you don't even know what I'm going to write down here.
No, but I know what you're writing down.
You know what I'm writing down?
Yeah.
This way, I would take the derivatives.
And then use the other one to the integral.
Yeah.
That's right.
And then going that way, I would do integrals. That's the way I would look at these. Derivatives going that way, integrals going the other way. So if I was given a problem, I need to pay attention. Am I given position? Am I given velocity? Am I given acceleration? Is my question asking me to get to position, velocity, or acceleration? Okay?
So the last one was asking for the highest. It's just t equals 6. That's it.
Yeah, that is the answer. Because that at t equals 6, what's its position? 100. Whereas the other ones, they were critical points. They were relative max and relative mins, but they weren't the absolute max, right? Okay, you guys okay? I know it's a lot, but does it make sense? Can you make that connection? Now, just because you know this idea, doesn't mean that you'll always, that I was about to word that very, very poorly. Sometimes they like to do things like this, where this will be one quick example here. Let's say I have here the velocity. This is some random problem I'm making up, so I don't know if this is going to work, but let's just say this does work. Let's say I have a velocity function, and this velocity function is going to equal to 2 sine of t. Okay? So this velocity is going to be traveling forward, then backwards, then forward, then backwards, because that's how sine function moves, yeah? If I were to ask you, what is the average velocity from 0 to pi? Do you remember the function that helps you calculate the average value of a function? Yeah, that's the mean value theorem. Do you remember how do you calculate the average value of a function? Ooh, ooh, ooh. I like that. I like that. Yeah. Hold on a second. S of t of 2 minus S of t of 1 over t of 2 minus t of 1. This will help you get the average velocity. But here's the problem. Here's the problem. Here's the problem. This right here is what? Position function, isn't it?
Yeah.
What's this one?
Velocities.
Oh. 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 Oh, here, let me give you this. At the start, when the initial start is going to be at 0 for its position. Now, you ready? I like this. You remembered this equation. Average velocity is the change in position over the change in time, isn't it?
Right.
Oh, so I just need the position function, don't I? Well, how the heck am I going to get the position function?
Take the integral
Of
of the
0 to
velocity
pi.
function.
e of t dt? Not even from 0 to pi. I just want
okay.
I just want the function, right?
Yeah.
Well, what's the integral of the velocity here? Help me out.
2 sine theta.
Try it. Do it. Work it out. Give me the answer. It's going to have a plus c involved, isn't it?
Yeah, because you gotta use substitution.
But isn't the plus c just 0? Or no?
It might.
Wait, you gave it to us.
It might. Well, give me first of all, what's the integral here? What's the integral of 2 sine t? Come on.
2 cosine, negative cosine.
Negative 2 cosine t?
Yeah.
Plus what?
Plus c.
This is my general position function. I still need to find out what c is, don't I?
Yes, you do.
So how do I find out what c is? What are my numbers here?
Equals c.
0 and 0.
0 and 0. Where do those zeros go?
X and y.
What are my x and y in this problem?
T and t.
S of 0 is equal to 0. And yes, you are correct. T and S of t.
Yeah.
So when t is equal to 0, I have here 2 cosine of 0 plus c is equal to 0 because S of 0 is 0. So help me out. What is this going to become? What's cosine of 0?
0.
No.
I mean, no, it's 1. I mean, 1.
You're right. So we got here 0 is equal to negative 2 times 1, which is just what?
Negative 2.
So what's C equal to in this problem?
1.
Yo.
Did I? 2.
2. What?
Oh,
You
you
add the 2
subtracted.
from both sides.
Yeah. You're too excited and you're getting through that. So here's the thing. I did the integral and it gave me a position function. Yes? And then they had an initial condition which helped me find out what my C should be equal to. So what is my position function equal to? S of t is equal to negative 2 cosine of t plus 2.
Plus 2. Plus 2. 2 is the C.
Yes, you are correct. Oh God, we're still not done though, are we? We just found the position function. What are we supposed to find?
The velocity.
The average velocity from what to what?
0 to pi.
So, what do I do?
Take the interval.
No, what? We just plug in the values, right?
Yeah.
So check this out. Up here, we have negative 2 cosine of what value? What's going to go in for cosine?
Pi.
Good. Yeah. Minus negative 2 cosine of what?
0.
0. Good. All over pi minus what?
0.
This right here, this is the average velocity, isn't it?
Yeah.
Go ahead.
So, are you doing, that line that you put and you put 0 at pi? Is that what you're doing?
Maybe.
Or are you just plugging in t?
I'm just plugging in t sub 1 and t sub 2 into my position function.
Oh, okay, I see. That's the function. Oh, that makes sense. Thank you.
Oh, we're almost there, I promise. What is cosine of pi?
0. 1.
Try again.
Negative 1.
Negative 1. So negative 2 times negative 1 is going to give me 2. Yeah? Positive 2. Cosine of 0 is 1. 1 times negative 2 is negative 2, but minus and a minus, this becomes a positive 2. And what's what's pi minus 0?
Pi.
So my answer is going to be 4 over, that's the average speed, or I'm sorry, not the speed, average velocity, I should not say speed, average velocity from 0 to pi.
Whoa. Is that the answer?
Yeah.
Wow.
All that work to find
I
out.
mean,
Yeah, if there was only some kind of easier way that I taught you to calculate the average value of a function.
it's an integral.
Yes, it is an integral. Do you remember the integrals that dealt with average values?
1 over
Yeah,
b minus a.
1 over b minus a times
So
what?
the mean value.
Oh, integral from a to b.
Of whatever function you're dealing with. In theory, this should give you the average value of that function.
Yeah.
What's the function I originally gave you?
Negative sine 2 sine 2.
So if this is my function that I'm trying to find the average of, couldn't I just necessarily do this average value function to this? In theory, it should work. So if I do 1 over, what's my b to a, by the way, in this case? It's still what? 0 to, so pi minus 0, yeah? Do the integral from 0 to pi of 2 sine t dt. It should be the same as that, shouldn't it? And it is. So I end up with 1 over pi times the integral of this thing, which is what we already did this integral, right? 2 cosine of t. No plus c because we're going to evaluate it from 0 to what? What does that mean? We plug in the 0 and we plug in the pi. 1 over pi times negative 2 cosine of pi minus negative 2 cosine of... Bro, isn't that the same thing that we just wrote down?
So then what's the point of this?
Nothing, they're the same.
So then
Yeah,
we
they're
just
the same.
choose? Oh, okay.
So, I had friends who had trouble memorizing this average value function, right? That tells you the average value of any function you need.
Yeah.
So, it's okay if you don't memorize it. You just have to do a little bit more work, right? if you're looking for the average of something, you just do the slope. Remember that? That's all a slope is. It's the average from here to here. But if I already have the function in hand, why go through the extra steps of finding this function right here when all you have to really do is just that? Now, both are fine. You'll get the answer either way, but it's up to you. Do you want to work the easy way, but it requires you to memorize this equation? Or do you want to work with a little bit more steps, which requires less memorization? You still have to have some memorization, though. Some would argue you've got to know this equation.
Yeah.
That's kind
Which-
of an ingrained in your
Which hopefully it is, because that's just y2 minus y1 over x2 minus x1, if you want to break it down that way. It's the same stuff. They just label it different things. Okay? How do you feel? Confuzzled? Sleepy? Me too. Me too. You're okay though, right?
Yeah.
Okay. So this is an application of integrals, right? It helps you get from one function to the previous function, yeah? There's also another application of integrals, and that's what I'm going to start this section with. You ready? 7.2.
Oh, we're done?
Yeah. It's a short one, but it's one that you need to know. Position, velocity, acceleration, all interconnected, right? In their own little way. Okay, what am I doing? Okay, so, boop. 7.2 is going to be some more applications of integrals, right? But we're going to do it, how do I want to title this? Yeah, sure, why not? You know what? No. More applications of integrals. All right. So this one, again, will be a little short as well, but it's basically the same kind of concept. You understand you have position, velocity, acceleration, right? But you also know that integrals is a thing that accumulates. It adds up from one time to the next time. It adds up how much of something has happened. So the first example I showed you with integrals, I usually involve like speed. If I told you, hey, this thing is traveling at 60 miles per hour, right? You draw that line, it'd be your graph at 60, right? And I told you, hey, this person traveled for 2 hours. How far did they travel? If they were going 60 miles per hour for 2 hours, they traveled 120 miles. No, just miles, right? Then I showed you like, yo, that rate stuff works for random things. Like for example, if a printer is printing out 5 pages per minute, how many pages gets printed out after 3 minutes? 15 what?
Pages.
15 pages, right? So when you have a rate and you deal with an integral of that rate, you can find out the total of whatever the top part of that rate is. You have pages per minute, your answer comes out as pages. You have miles per hour, your answer comes out in miles. So if you have a rate of something changing, when you do the integral, you can find out the total of something over a specific time. Crazy stuff. Why am I saying this? Well, we did some stuff with like snowfall last time. Do you remember that?
Yeah.
Now we can do it with calculating integrals of these things. We've already done this. This is a slight review, okay? So it's just an application of these integrals. And then I promise you we'll get away from these applications. All right, I'm going to give you, I think this is a good problem to do. Oh, God. I hope this works. I don't know if this is actually going to work. No, I'm just copying some. No, it's not going to work. I'm copying a old test problem from the actual free response section of the AP Calc exam. So let's actually take a look at this one. I don't think we'll actually be able to do it because of time, but you know what? It'll be okay. Here is the problem. This was actually on the 2010 AP Calculus free response question number 1. It was 12 years ago. Copy it. Yeah, copy that down. What's beautiful about question 1 and question 2 on the free response question is that they're calculator questions. So you have to still write stuff down, but you don't actually have to do the integral by hand. You know, like integral, cosine, and sine though are pretty easy. But when they give you the calculator problems, they're always going to give you some kind of crazy function. Like, do you see the function on this one? You guys see it?
The piecewise function.
Oh, just piecewise?
I'd copy down the piecewise, but I'd copy down the words too if you really want a full set of your notes. But honestly, this is all posted online, right? You could always just copy it later.
So you recommend the words as well?
I would, but you don't have to do it right now.
I'm just gonna like really write fast.
Okay.
What's the function?
Who cares about legibility?
Or do you have to like narrow it down? Oh, it's 7t e cosine.
So we got a couple of functions here, don't we?
Yeah, they're definitely.
Snow accumulates in the driveway at a rate modeled by f of t. So we got that function. It's equal to 7t times e to the cosine of t, cubic feet per hour. T is measured in hours since midnight. So when t is equal to 0, it's midnight. When t is equal to 1, it's 1 a.m.
Low-key, Janice can solve her own problem.
T is measured in hours since midnight. Janet starts removing snow at 6 a.m. The rate at which Janet is removing snow is labeled as g of t. So there are two functions. One is snow falling, and one is snow removal. G of t is how fast Janet is removing snow. In cubic feet per hour, at which Janet removes snow from the driveway at time t after midnight is modeled by here. So from 0 to 6 a.m., Janet's not removing any snow, is she? From 6 to 7, she's removing snow pretty fast. She's going at 125 cubic feet per hour. I don't actually know how fast that is, but I do notice this though. After her first hour, what happens to her rate? She slows down. Ugh. This person's getting tired already after an hour. Ridiculous.
We live in California.
There's snow in California.
Well, we know that you live there.
Poor Janet.
I'm thinking of the good place.
Also thinking of the
I'm just not gonna think about it and just keep charging it away. Alright, so we got two functions here. How many cubic feet of snow have accumulated on the driveway by 6 a.m.? Do we need g of t for this question? G of t talks about removal of snow, whereas this is asking how much has been added at, how much has accumulated by this.
125.
No.
It's not simple.
We can't look at the 125. This is how fast it's being removed.
Yeah.
It doesn't necessarily mean it removed all of it.
Oh yeah, because there's probably more.
Do we have a function that tells us how fast the snow is falling?
Yes, we do. Gotcha.
So I'm going to give you a second to try to just set up this answer. What do you think you would write down to set this up? Come up with an idea of what you would write down for your answer for this one?
So the interval, is it
Yeah, how much snow has accumulated on the driveway by 6 a.m.? Remember, we're starting at midnight,
Yeah.
and T is measured in hours. No. She started removing snow at 6 to 7. That's why there's 0 there. So, also, we're not talking about the removal of snow. We're just talking about how much snow has accumulated, how much has fallen. What's the function that deals with the snow falling? So we're just looking at f of t in this case, aren't we? 7t times e to the cosine of t. That's the function you really want to focus on. Because we're focusing on how much snow has fallen. We don't care about the removal of snow yet. So what would you write down to find out how much snow has fallen, given that this is the function? Integral? Is it from 12 to 6?
6 to 12.
Is it from 6 to 12? 0 to 6. Why?
You don't count 12?
You do. But 12 is your starting point.
Yeah, isn't it how much is falling?
Yeah. And what's t equal to at 12 o'clock?
0.
There you go.
Yeah.
12, the number is just a label, isn't it? Yeah. Even the 6 itself is just a label, but the time that it travels to it is 6 hours. They really want to mess with you. They would say snow started falling at 3 a.m. What's the accumulated snowfall at 6 a.m.? Your integral on that one would not be from 0 to 6.
0 to 3.
It would be from 0 to 3.
Yeah.
Because it's from 3 o'clock to 6 o'clock.
And then the time at 3 is 0 and 6 is 3.
Yeah. But this one they didn't mess with you. They just said, 12, make that 0, go to 6 a.m. So it goes from 0, which is 12 a.m., to 6, which is 6 a.m. Of what?
The 7t e cosine t.
Good. And if you wrote this into the problem, you would get 1 point.
Yay.
It's the easiest point ever.
That's it?
The other point would come from you getting them the numerical value, which you would just plug into what? Well, the calculator. So let's finish this off with this part right here. I'm going to plug this in. How do you do the integral on a calculator?
Math 9.
Math 9. Good. This is going to go from 0 to 6. What's the function that we're dealing with? 7. T. In this case, it'll be x. What else? E. Do you guys remember how to get to the E button? It's right here over the ln, so you have to press the blue button, then press ln. E to the what? Cosine of x. Close that parentheses off and bring that down. And what is this with respect to? X in this case, but t in our case, right? Press enter. 142.275. Now, look at this problem. Look at the question. Notice they give you the units. Do you guys know how to write cubic feet?
Feet.
Yeah. If the problem specifies that you need units, write the units down. If it doesn't say specify the units, don't write the units down. Yes. If you write it down correctly, they're not going to mark you off on it because you did it. But if you mark it down wrong, even though they didn't ask you to write down the units, they will take away that point, even if you get the numbers right. So if I had written this down and wrote down feet squared, because I for some reason forgot that volume was cubic, I would get this mark wrong, even if my numbers were the same. This problem is a very easy 2-point problem. Write down the integral, write down the answer. You get 2 points out of 9 on this free response question. Just a heads up, if you can earn, on average, 2 to 3 points per free response question, you can pass the AP exam with a 3. There's 4 parts to this, but we'll talk about the rest of them later. Just wanted to show you, this is it. These are these types of free response questions on there, and I don't want you to stress out about them. If you can't do more than half of it, if you can just at least get 1 point or 2 points, you'll be good. Okay? All right, we'll stop there.